In this video, we'll be focusing on solving exponential equations. Now, before we can solve an exponential equation, we need to actually know what an exponential equation is. And an exponential equation is simply an equation where variables occur in the exponents. So we have three different examples below. Notice here, variable in the exponent. Here, variable in the exponent. Here, two variables in the exponents. So we're going to talk through strategies that we can use in order to help us to solve these types of equations for the missing variable value. So to start, we're going to look at a simple exponential equation. And while this looks difficult to solve to start, what you're hopefully noticing is that both of these have a base of 3. And what we're saying here is 3 to some power is equal to 3 to the power of 8. And what you're hopefully thinking about is the fact that we have 3 raised to some power, and we're saying that these are in fact equal. So 3 to some power equals 3 to the power of 8. Well, in order for these to be equal, the only way that they can be equal is if this chunk right here is equal to 8. If this chunk right here is equal to any other number, it won't be an equation, because the only thing that equals 3 to the power of 8 is 3 to the power of 8. 3 to the power of 8 can't equal 3 to the power of 5 or 3 to the power of 6 or something else. So what we can do if we have the same bases here, so notice that we have the same base. If we have the same base with this equal sign in between, what we can do is we can actually set their exponents equal. So if we have that same base, we're saying 3 to the power of something equals 3 to the power of something, then the only way that this equation will be true is if those two exponents have exactly the same value. So we can set them equal to each other and then solve, just like a normal one variable linear equation. So here we subtract 20 from each side. We have 4x is equal to negative 12. Divide both sides by 4, divide both sides by 4, and we find x is equal to negative 3. So here we find that if we take x is equal to negative 3 and we substitute it in here, we would get 3 to the power of 8 on both sides. So now let's use this same thinking to solve the two examples below. What I first notice in this first example is that both of these have a base of 7. So in order for this equation to be true, if these have the same base, then their two exponents need to have the same value in order for 7 to some power to equal 7 to some power. So I can take my two exponents and set them equal. And then from here, simply use my knowledge of solving equations to solve. And I find that x equals 6 will essentially result in this left-hand side having an exponent that is equal to 20, so that 7 to the power of 20 is equal to 7 to the power of 20. Then if I look at this next side over here, I notice that I have multiple x values, but what I do have in common is they both have the same base. So while I don't know what that exponent is actually equal to, since they have the same base, I know that they have to have the same exponent regardless of what that exponent value is. So I can take both exponents and set them equal. So I have 3x plus 5 is equal to 8x minus 45. So I start by getting all of my x's together on the same side. So I have 5 is equal to 5x minus 45. Now I can add the 45 over, so we have 50 is equal to 5x. Divide both sides by 5, and I find that x is equal to 10. So what I can then do is I could take x equals 10 and plug it back in here. So I find that this exponent is equal to 35, as is this exponent equal to 35. So that x value equals to 10 makes both of these exponents equal 35. So I have 9 to the 35th is equal to 9 to the 35th. So now let's take a look at what happens when we have two equations, but the bases aren't the same. So if we take a look at both of these equations, what we notice is that both of these equations contain an x value inside of the exponent. So what that tells us is that because of this x value in the exponent, we're going to have to use some of our exponential equation solving strategies to help us solve these, because we can't just remove the x from the exponent without actual probable cause and logical thinking. So what we're going to do here is we're going to think through what we can do. And on the previous couple slides, we learned that if we have common bases, so if we have two numbers down here that are the same with an exponent, we can actually just set those exponents equal to each other and solve the exponents being equal to each other. Now, when I look at this first example here, I see that I have a base of 5 and a base of 625. And unfortunately, those two numbers are not the same. So written as is, I cannot just say, I'm going to set, 2x plus 6 equal to, this is really 625 to the power of 1. I can't just set 2x plus 6 equal to 1 because the bases aren't the same. But what I can do is I can use my powers resource and try to do some very purposeful rewriting. And if I look at my powers resource, what I notice is that 625 is the same thing as 5 to the power of 4. So 5 to the power of 4 is 625. So what I can do is I can substitute 5 to the power of 4 in place of 625. So instead of having 5 to the power of 2x plus 6 is equal to 625, I can say that 5 to the power of 2x plus 6 is equal to 5 to the power of 4. I can substitute in something that is equivalent. So by doing some very, very purposeful rewriting, I now have bases that are the same. And if I have bases that are the same, I can take the two exponents and I can set them equal to each other. And then from here, all I need to do is solve. So I subtract 6 from each side to end up with 2x is equal to negative 2. Divide both sides by 2, and we have x is equal to negative 1. So now the idea, if we don't have common bases, we're going to try to create common bases. Now, if I take a look at this next one over here, I see that I have 4 to the power of x and 2 to the power of x minus 3. And again, we have a situation where these two bases are not the same. However, if I start looking at my powers resource, what I notice is that 2 squared is equal to 4. And because 2 squared is equal to 4, what I can do is I can take 2 squared and I can write it in place of 4. So here I have 2 squared to the power of x. Notice that I just replaced 4 with 2 squared. And that's equal to 2 to the power of x minus 3. Now, this is very, very close to being done. However, I need to be careful here because I still have these parentheses here. The 2 is inside parentheses and the x is on the outside. So what I can do here is I can say, well, I can combine these exponents together by using that powers to powers rule. Remember, when we have a power raised to another power, we multiply them. So this is really 2 times x. So we have 2 to the power of 2x. And that's equal to 2 to the power of x minus 3. And then from here, I can say, well, hey, I now have common bases. And so as a result of that, I can take my two exponents and I can set them equal to each other. So here I can subtract 1x, and we get 1x is equal to negative 3. So let's try one additional example here. So again, we can see that we have two bases that are not the same. And because these two bases are not the same, and we notice that we have variable values inside of our exponent, because of that, we have to start thinking about how we can get these bases to potentially be the same. So what I notice when I look at these and when I look at my powers resource is there's a relationship between 4 and 64. What I notice when I look at my powers resource is that 64 is equivalent to 4 to the power of 3. So what that means is that in place of this 64, I can write 4 to the power of 3. So that's what I'm going to do. I'm going to replace 64 very purposefully with 4 to the power of 3. And then, as a result, I'm one step closer to having common bases. Now, when I look here, what I notice is that it looks like this exponent might be a little bit messy. We have to use the powers to powers trick here to multiply this out to be one exponent. And because there's two terms over here outside the parentheses, we have to multiply 3 by both x and the negative 2. So this becomes 4 to the power of 3 times x, which is 3x. And then minus 3 times 2, which is negative 6. So here you'll notice, after some very purposeful rewriting, I now have two bases that are the same, two bases with 4. And now I can take each exponent, so 3x minus 6, and set that equal to 2x. Now my goal is to get my variable value by itself, so I subtract 3x from each side. And as I do that, I end up with negative 6 is equal to negative 1x. And then I need to get that x by itself, so I divide by negative 1, and I find that x is equal to 6. So if I were to take this 6 and substitute it back in here for both of these variables, I would find that my equation is true.